Please take your seats. Our program is about to begin.
Good morning, everyone. I take great pleasure in welcoming you all to the Federated Computing Research Conference this year, the 9th such event in the history of this conference series. Yesterday was Father's Day. Congratulations, or happy Father's Day. And today is Juneteenth, a federal holiday here in the United States. I especially thank those of you who celebrated these special commemorative days here with us, choosing to come to FCRC 2023. Thank you. I am Timothy Pinkston, professor at the University of Southern California in Los Angeles, and it is my honor and distinct privilege to serve as the FCRC chair this year. My preferred pronouns are he, him, his. FCRC started 30 years ago, back in 1993, initially convening every 3 years, until it transitioned to convening every 4 years, starting in 2003, that's 20 years ago. As you know, FCRC brings together many affiliated research conferences and associated workshops during this week-long co-located event. This year, we are happy to host 14 different conferences and symposia and 2 Computing Research Association, CRA, independent workshops. This past weekend, we welcomed the start of LCTES, ISMM, and SPA. Today, we welcome the start of ISCA, EQUAS, and PLDI conferences. I'm happy to report that nearly 2,600 total attendees have registered for FCRC this year. Beyond the exhilarating technical conference and workshop talks, the serendipitous networking opportunities, and the interesting cross-interactions that attendees can have with persons from various technical and areas and backgrounds, FCRC hosts plenary sessions on topics of broad appeal given by leaders in our computing community. We hope you'll enjoy this year's FCRC and will indulge fully in all that this year offers. In so doing, please be mindful that FCRC promotes openness and inclusiveness. FCRC is a safe place for rich intellectual discourse, for free exchange of research results and ideas, for open scholarly interactions. We support and welcome a welcoming environment for all to thrive that lives up to ACM's core values, which promote diversity, equity, inclusion. We're grateful to have a CARES presence here at FCRC, the Committee to Aid Reporting on Discrimination and Harassment Policy Violations. CARES members are available to anyone who may experience any unacceptable behavior, which we firmly stand against. Thank you, CARES, and for other organizations and committees such as CARES. Thank you. You care, and I trust that we all care. I also thank all of the conference leaders for their dedication and hard work in helping to make FCRC highly successful this year, and thereby continuing the rich history of this federated conference event. I thank all of our corporate sponsors and academic FCRC sponsors for their generous support this year. Our FCRC sponsors include FutureWay Technologies and the USC Viterbi School of Engineering at the platinum level, Google at the gold level, Meta and Samsung at the silver level, and Alibaba Cloud, Amazon, Pathway, Springer, VMware, and the University of Virginia School of Engineering and Applied Sciences at the bronze level. Let's give a hand for all of our sponsors. Of course, I also thank all of the sponsoring ACM SIGs for their support and cooperation. SIG Act, SIG Arch, SIG Bed, SIG Energy, SIG Metrics, SIG Ops, SIG Plan, and SIG Sim. I also thank the FCRC Steering Committee for the wise counsel and guidance that they've been giving me. Vivek Sarkar is the chair of this steering committee. Thank you, Vivek, for all your guidance and advice. I thank the ACM, especially Donna Capo, and the executive events conference management team, led by Jillian, for helping to ensure that this conference is a success, unfolding in a very organized and smooth way. Thank you, Jillian. I'd like to acknowledge the presence of the ACM CEO, Vicki Hansen, and the Chief Operating Officer, Pat Ryan. Please stand. Thank you for your support. Finally, I wholeheartedly thank Dilma Da Silva, our FCRC Plenary Speakers Chair, for putting together such an outstanding set of plenary sessions, including, for the first time in the FCRC's history, a plenary panel, which will occur tomorrow afternoon, which we hope you all will enjoy. Note that all plenaries, including this one, is live streamed through our FCRC website. So with that said, these opening remarks, I'm happy to turn the podium over to Dilma.
So hi everyone, as Tim said, I'm Dilma Da Silva. I'm chairing the plenary speakers part of FCRC. I'm from Texas A&M University, and I'm currently serving at the National Science Foundation. My pronouns are she, her, hers, and it is my honor to introduce our first speaker. And sorry if I'm speaking too loud and reverberating, it's my teaching voice. So Professor Kunle Olukotun is the Cadence Design Professor of Electrical Engineering and Computer Science at Stanford University. He's a pioneer in multi-core processor design. He founded Afara Web Systems to design high-throughput, low-power multi-core processors, and those processors now power the line of servers from Oracle's, the ones based on Spark. In 2017, he founded the SambaNova Systems, a machine learning and artificial intelligence company that he is still leading. He has received a lot of awards. I'll just mention a few of them. He's a member of the National Academy of Engineering. He received the Harry H. Good Memorial Award, and he recently received the 2023 IEEE Computer Society Eckert-Mockley Award. I have just one more comment. So before we get to the talk, there are microphones on stands on the aisles on the side. So you'll be able to queue for questions in the Q&A session of the talk. So thank you so much, and join me in welcoming Professor Kunle Olukotun.
Good morning, everybody. Thank you to Dilma for that wonderful introduction, and to the organizing committee of the FCRC for inviting me to give this plenary talk. The title of my talk is Computing in the Foundation Model Era. And let me begin by talking about foundation models, right? So everybody in the room is familiar with foundation models because everybody has played with ChatGPT, right? So the models behind ChatGPT are these huge models with billions of parameters. They've been like GPT-3, GPT-4, and then other models that generate images like Midjourney and Stable Diffusion. And they're trained on huge amounts of data, both text and images, and some of them are trained on speech. And they learn some very interesting representations that give them amazing capabilities. One such capability is the idea of in-context learning. So this is a property that blows up the whole idea of task-specific models that existed before the foundation models came along. And the idea is that you can use the same representation with minor customization using text, using English language text. No longer programming is required, and you can get amazing accuracy on all sorts of tasks that you never specifically trained the model for. And so, you know, what happens now is you can develop new applications in days with undergrads, what might have taken weeks or months and years with PhD students in the past. So, you know, these foundation models are going to have wide-reaching implications to both technology and society. And there's the Center for Research on Foundation Models being led by Percy Liang at Stanford that's investigating what impact they'll have. So what are some of the impressive things that you can do with foundation models? Well, you know, of course, you can generate text, all sorts of text generation possibilities. You can write code in fairly obscure languages like Verilog. I'm a hardware designer, so I sometimes write Verilog, or maybe my students do. And you know, you can actually get these models to generate the code, and oftentimes it's correct, sometimes it's got bugs. But if you give it bugs and you ask the model to correct the bugs, it will tell you how to correct the bugs and tell you, you know, why the bug occurred. You can generate art with these models by using, again, English language prompts, and you can get pretty good pictures. Here's one from Stable Diffusion from New York, and it looks pretty good, much better than I could do. And then, of course, you can also use it for scientific purposes, like trying to predict how proteins and RNA folds. So AlphaFold is being used to design drugs. And I was recently at a conference, and somebody said, well, the equivalent of ChatGPT for the biopharma was AlphaFold. So it's having a tremendous impact, and it's going to, you know, transform what we can do. So to attain these capabilities over the years, the models have been growing in size, right? So they started out, you know, with BERT large, which by today's standards should be called BERT tiny teeny. And they grow up to models of the size of 500 billion parameters, like Megatron, right? So that's sort of a 1,000-fold increase in size in 3 years, 10-fold or an order of magnitude per year. And so over time, as you train these models with more data and with more parameters, they increase in quality, but they also substantially acquire new capabilities. For example, they can explain jokes. So here's a joke. I tried 10,000 random restarts of my neural network, but I was accused of overfitting. I guess no good seed goes unpunished. So you give this joke to a 1.3 billion parameter model, and it basically repeats the joke and doesn't really explain it. You give this joke to a 175 billion parameter model, and it tells you that, in fact, this is a play on the phrase, no good deed goes unpunished, and tells you, why this is funny. And so you get these step functions in capability with increasing parameter size. And so, of course, as you increase parameter size, you also dramatically increase the computational requirements for training and inferring these models, right? And so, roughly today, it's 200 teraflops per parameter once you get, to the 200 billion regime. So for a systems designer, the question then is, given the increasing importance of foundation models, how do we design systems that are both enable these models to scale and also, of course, scale efficiently? Because, of course, we're in this regime where performance is limited by power, and so everything has to become fundamentally more energy efficient, and the models themselves have to be efficient. And so if we can scale these models by another 2 or 3 orders of magnitude, then we can potentially unleash new capabilities. But maybe more importantly, we can allow more people to have access to these models, because the models that we see today that are already very capable then could be attainable to people with much fewer resources. And so this would be an important in democratizing the accessibility to foundation models and making more organizations and more researchers capable of doing work in this area. So not only are these models scaling, but these models are not fixed, right? So machine learning researchers continue to innovate in the algorithms that they are developing for these models. And so we need to provide a way of not only making them more efficient. So one of the ways that you could potentially make them more efficient would be to take a algorithm and cast it directly in silicon as an ASIC device, but then it would no longer be flexible. And so the question is, can we attain both high efficiency, the efficiency that you might get from a very customized ASIC, together with the flexibility you might see from a general purpose computing device? And we think the answer to providing both scale, efficiency, and flexibility is to have a vertically integrated co-design of innovations in ML algorithms, innovations in data flow compilation environments and compilers, which are kind of the core to the execution model of these machine learning algorithms, and then new hardware, reconfigurable data flow architectures, which are specialized for executing data flow models. And so for the rest of my talk, I'm going to go through each of these individual components and show you how they work together to provide dramatic improvements in the support for these foundation models. Let's start with ML algorithms. So as many of you know, the key component of most of these large foundation models is a transformer-style architecture. Basically, the ML world has decided that this is the architecture that they are going to focus on because it provides high accuracy on a wide range of tasks. And as many of you know, this is a stacked encoder-decoder architecture where the heart of it is this algorithm called attention. Attention allows you to draw connections between different parts of a sequence of tokens. So for instance, it can tell the difference between, it knows that in the first sentence, it refers to the dog, and in the second sentence, it refers to street, right? So it can learn these connections. And the key to doing that is this QKV query key value input, and the idea is the attention mechanism learns the correspondence, the mapping between a query and a key value pair. And this is computed as a weighting sum. And so the key thing to know is that, typical sequence lengths are in the 1K to 8K token range. And what one would like to do is increase the sequence length capability of these attention algorithms by an order of magnitude, or maybe much more. And so the question is sort of, why is this important? Well, the sequence length determines the context which you can give to the model, right? So if you have only, 4 to 8K tokens, then maybe you can only do 10 or so pages of text. But if you have 100K tokens, and maybe you can do books or plays and much longer legal documents. And so much greater capabilities are provided by longer sequence lengths. The other thing that's also possible is you can actually analyze images at full resolution. So the images you take with your mobile phones have resolutions which are much higher than most of the models that are used that are actually in use. And so the question is, if you could get better, high resolution models, then of course you have more robust insight into whatever you're trying to do with these image models. And then you can open new areas. There are lots of things that are important, such as time series, video, medical imaging data, and genomics data can be modeled as a sequence of tokens. And so what you need to do, of course, to analyze this data is be able to deal with much longer sequence lengths. So let's look at attention and understand what some of the problems are and what we might do to actually improve the performance of the attention algorithm. So the key component of attention is this scale dot product calculation, right? Where you do a matrix multiply, masking, and then you do a operation called softmax. And so it's represented in the equation as, the softmax of the mask of the matrix multiply. And so attention is slow because essentially what you're doing is a quadratic calculation which takes quadratic space and time. And so this shows pictorially what happens. First you create the attention matrix, then you might mask, followed by softmax, drop out, and finally the multiplication times the value vector. And so the attention, as I said, is quadratic because you are creating these matrices. And so what happens is that the size of the matrix given the sequence length will not fit in on-chip memory. And so you're forced to constantly move the matrix data back and forth between the compute and the memory. And so what happens then is that this constant movement of data becomes the bottleneck to the performance of attention, and fundamentally, the size of the matrix that you can contain in your off-chip memory limits your sequence length. And so the question is, could you do better? Well, if you gave the flash attention algorithm to a smart student who took my computer parallel processing course, they would come up with they would in that course they'd learn about two key optimizations. And so Tree, Dow, and Dan Thu are PhD students who work with Chris Ray, who looked at this algorithm. And of course, many people had come to the conclusion that, in fact, it was memory limited, but they were the first ones to come up with a comprehensive way of fusing the different components of the attention algorithm together. And then, of course, if you fuse them, you still have this problem that the memory size of the matrix is still too big. And so the next optimization that which you would get from a parallel computing course would be, so that's fusion is one. The other would be tiling, right? So you would tile the matrix into pieces that would fit better into the on-chip memory. And then thereby you would get a much more efficient algorithm. Turns out there's one little wrinkle, which is you can't tile this computation arbitrarily because there's this softmax computation that requires multiple tiles in order to be computed correctly. And so in order to do this, then you have to know how to change the algorithm. So it's not a straight, you can't apply the principles of parallel computing directly to this algorithm and get it to work correctly. You also have to understand the algorithm and deal with this problem of softmax. But if you do that, now you can get a 2 to 4x improvement in performance on graphics processing units, GPUs, and a 10 to 20x reduction in the amount of memory required. So this is dramatic, and lots of people, saw the results of this flash attention algorithm and started using it, right? So if you use GPT-3 or if you use ChatGTP, you under the hood, you're using flash attention. If you if you look at OpenAI, they see dramatically longer sequence lengths are available, and again, a lot of this is due to the use of the flash attention algorithm. The open source folding algorithms are also using flash attention. So this is already having a dramatic impact on what people are able to do with these foundation models. So one of the ideas, for being able to scale the size of the model without increasing the amount of storage, memory requirements, or compute is to use sparsity, right? So this is an idea, of course, that goes way back in scientific computing. And so the notion was, well, why can't we use sparsity to train machine learning models? So lots of people have tried to do this, right? So the challenge is both getting the accuracy that you got when you trained your model using dense matrices, while actually speeding the computation up, or actually taking less time, right? So it turns out that there have been lots of ways of trying to find these sparsity patterns and maintain the same level of accuracy, but people have not been able to do this, right? They've tried all kinds of ideas, lottery tickets, hashing schemes, dynamic sparsity masks, but the net result is that they've slow down the training by a large factor, 5x or more in some cases, or they don't actually, or they lose accuracy. So unstructured sparsity, where you are looking at individual elements of the matrix being zero or non-zero, is the scheme that is being able to maintain the highest accuracy. But it turns out that unstructured sparsity is not hardware efficient. Hardware likes to work in blocks of computation because dense blocks are what you can make work well in terms of doing the matrix computations, and they also much better use the bandwidth that is that crosses the pins of a chip. And so two students at Stanford, B.D. Chen and Tri Dao, have come up with a scheme called pixelated butterfly. And the key behind pixelated butterfly are the idea of monarch matrices. And monarch matrices are a way of doing sparsity in a structured way, right? So instead of arbitrary points in the arbitrary locations in the matrix being zero or non-zero, the idea is to have blocks, and you've got this block diagonal representation, and the monarch matrix is basically a multiplication of two block diagonal matrices and two permutation matrices. it turns out that these monarch matrices are expressive. They can express any structured matrix, like a Fourier transform, sine, cosine transform. And they are hardware efficient because they use these dense blocks in terms of dense matrix computation and memory access. And so the question is, can you actually train ML models using these monarch matrices? So sparse training has been shown with these monarch matrices for image models, VIT base. And here what we see is we can use monarch and get the same accuracy for ImageNet classification, but now you actually get a 1.8 times speed up. So this is the first time that you actually see improvements in speed up with sparse training, while of course maintaining the same accuracy. Another way of doing sparse training is to train sparse for a large fraction of the time, but then switch to dense at the end of the training time. And so in this case, you're running for 80% sparse and 20% dense. Again, you are on GPT-2, you get a speed up of 1.7. And of course, GPT-2 is a language model. So these ideas, or these results are pretty promising. They haven't been tried on the very largest models yet, but we are certainly into the billion parameter model size, and they are showing very encouraging results. So the question then is, could you actually get rid of this quadratic attention algorithm, right? So as I said, attention is important for being able to come up with this correspondence between elements of a sequence. And the question, can you do this without attention? And so again, using monarch matrices, there's the idea of monarch mixer, which is a new paper by Dan Fu, showing that actually you can use these monarch matrices to get the sort of mixing that you need to make these models work, and showing an improvement of in speed up of 5.4 on BERT. So it's on BERT image models, and on GPT, you are not getting speed up, but you're at least matching the accuracy. It turns out that GPT is actually a more difficult model for this kind of approach to work. Then lastly, another way of getting rid of attention is by using what are called state space or signal processing methods. There's a set of papers, based on these types of models. One of which they're called hyena models, and I kind of tell you have to ask the graduate student why he named them hyena. But the key idea then is they're both attention-free and so subquadratic, and they've been shown to scale to hundreds of thousands of tokens, and million tokens experiments are in process. So because they're signal processing type algorithms, the core computational component in them is FFT, fast Fourier transform. And FFTs, in fact, don't work very well on current ML accelerator hardware. And so the question is, is FFT going to be more important as a component of hardware going forward? So the point being that, as I said, accelerator hardware for ML needs to be flexible because the algorithms are changing. So last point I'd like to say about algorithms is that, ML models are data flow. Right? So, you get the models are developed using these frameworks, PyTorch and TensorFlow, and what you get out is a data flow graph of ML kernels, matrix multiply, convolution, pooling, and then the connections between them, of course, are the tensor data. So, data flow then is a core component of these algorithms. So let's think about how a compiler might optimize the data flow in these algorithms. So you start with a representation of your model in one of the frameworks, PyTorch or TensorFlow. And then what you get out is this graph of operators. And then the question is sort of how do you execute that efficiently, or how can you translate it to be something that could run efficiently on an accelerator? And so we spent a lot of time thinking about how to develop compilers for various architectures and accelerators. And one of the conclusions we came to was that a core component of the intermediate representation of the compiler should be what we call parallel patterns, right? So parallel patterns are, these operations that tell you about both the computation and the data access patterns, and they're ones that you're very familiar with: map, zip, reduce, flatmap, and group by, and they operate on collections, right? There's no parallelism without operating on data types that have multiple elements. And you can convert all these data flow graphs from at the machine learning abstraction level into these hierarchical data flow graphs of parallel patterns. And then you can optimize at this level to improve parallelism, right? You can optimize in various ways. You can optimize, you can do tiling, you can do fusion, you can do a technique called meta pipelining. And one other point is, of course, you can also represent SQL using parallel patterns. And then, as I said, you can do fusion, tiling, meta pipelining, which is a form of hierarchical pipelining, and I'll say a bit about that in just a moment. And then you might generate some intermediate representation, which is close to the accelerator that you want to execute your machine learning algorithm on. And so we came up with one which is based on parallel patterns, and it's this parallel patterns expressed as a hierarchy of tiled pipelines and with an explicit memory hierarchy. And this is expressed in a language we call spatial. Some more recent work that we've been involved in is to create a sparse abstract machine for tensor algebra and streaming data flow. So this is work by Olivia Hsu and Max Strang. And the idea is to represent linear algebra kernels expressed as einsum, shown in the middle. And then with a combination of the data formats and the schedules, you can create this intermediate representation, which consists of composable primitives and a format for the tensor data that strings between these primitives. And so you can compose these primitives, and you can use this intermediate representation to explore the design space or to map to lower level accelerators, to map to accelerators, such as a reconfigurable data flow accelerator, which I'll say a bit more about, and the compiler for doing that is called Stardust. So if you want to incorporate compilers like Stardust or other optimized libraries, some very recent work presented at FCRC this morning is the idea of Mosaic, which is an interoperable compiler for tensor algebra. And the lead author of that is Manya Bansal, who's an undergrad at Stanford. So she has a award-winning paper, and she hasn't even graduated yet, or maybe she graduated on Sunday. And so, and this paper basically allows you to take these Einstein representations and take components of them and map them to existing libraries. And it can do this automatically, and it can allow you to expand to explore the design space, and it can fill in the bits of the expression that are not handled by the library. So you could map them to MKL, to BLAS, or you could use a compiler like Stardust. So, a while ago when I was, working on architectures of various sorts, I remember a quote by Jim Smith who used to be a professor at Wisconsin, and he said, if you have a vector problem, then you should build a vector computer. So we have a data flow problem, so we should build a data flow computer. So this is what we set out to do, and we call it a reconfigurable data flow architecture. And the reconfigurable data flow architecture is designed to execute parallel patterns expressed as spatial. So you see the co-design between the compiler and the intermediate representation and the architecture that is going to execute it. And the key components of this architecture are this tile array of pattern compute units that do the compute and pattern memory units that do the memory provide the memory access. And the two students who worked on it are Raghu, Prabhakar, and Yaxi Zhang. And it was presented at ISCA in 2017. And so let me tell you a little bit more about the pattern compute unit. The pattern compute unit is this reconfigurable SIMD pipeline. And so you have these input buffers which allow you to take data from the on-chip network, which connects all the different units together. And then you've got some number of pipe stages in depth to exploit pipelining and some number of lanes in width to exploit SIMD parallelism. So you can map a basic block to a PCU, and in this example, you map each of the operations to a different pipeline stage. And so the parallelism you can exploit is, of course, the product of the width in terms of SIMD and the depth in terms of pipeline stages. And of course, you're going to configure the PCU so you don't have to do instruction fetch every cycle. So you remove the overhead of doing that. And then, of course, you stream data into the PCU through the input buffers, and then there's an output FIFOs output FIFOs are going to be the input FIFOs of the next unit. The pattern memory unit is meant to supply data to the PCUs, and the key components of that are a highly banked set of a banked memory unit with the ability to supply the bandwidth to the for the requests for the loads and stores, and the ability to generate fairly complex address schemes to match the potential for the sparsity that you might have in your algorithm. So sparsity requires irregular memory access, irregular data access, and you support that sort of capability by using these dedicated address units. And then data, again, streams into the input buffers and out of the output buffers. So, you know, the idea then is that you can use an architecture like this to improve flash attention. And the way that you do that, of course, is you're going to take flash attention with its ability, with its fusion and tiling, and you're going to lay that out in space such that you can exploit pipelining between the different tiles, right? And so you also have data flow execution, which is controlled by tokens. So this reconfigurable data flow architecture allows you to exploit parallelism at these multiple levels within the PCU at the vector and pipe stage level, and then across multiple PCUs and PMUs using this meta pipelining approach. And as you see in the picture, you've got multiple tiles in flight because you've mapped the different components of the flash attention algorithm in space. So the point here is that by mapping your data flow graphs in space, you get the natural fusion of the data communicating on chip, and you also get this pipelining effect, which is shown in this picture, this meta pipeline diagram. And so, in this example, at tile 4, you've got 4 tiles in flight at the same time, and so potentially you get a speed up of a factor of 4. So the idea of sort of using plasticine as a way to exploit parallelism and enable the acceleration of machine learning algorithms worked so well that we decided to form a company, and this company was founded in 2017, and my co-founders were Rigo Liang and Chris Ray. Chris Ray is, of course, a colleague at Stanford. Rodrigo Liang I've known for many years. And so this first commercial example of a reconfigurable data flow architecture was our RDU, and it was called the Cardinal SN10. And those of you who know about Stanford know that all Stanford athletic teams are called Cardinal, right? So this was a 7-nanometer chip, had 40 billion transistors, so it was really a substantial chip, 640 PCUs with a peak of 312 BF, brain float 16 teraflops, and the support for other data types. And then 320 megabytes on chip with a lot of bandwidth to this on-chip memory because, of course, the memory is distributed. So how did the SN10 differ from the research ideas that we developed under the plasticine? Well, one of the things, of course, we did was we needed to support matrix multiply efficiently. So we converted we allowed a mode in which the PCUs could run in systolic mode so that they could do matrix multiply efficiently. We added some more data formats, and we added support in the PMU for doing data transformations. So this is pretty important to support reshape. So those of you who do machine learning know this is, you often need to change the shapes of your matrix, your tensors, and so the data align unit could support these kinds of transformations, such as transpose. We also augmented the interconnection network so that it wasn't just statically scheduled, so that it could be dynamically scheduled, and this made it much easier to develop different algorithms. In terms of the compiler, we made use of kernels, but the whole idea of using parallel patterns and data flow optimization was basically the same as we had developed under in the plasticine compiler. Now, of course, it had to be made much more robust, and it had to be able to be driven by PyTorch ML algorithms. And so, of course, there was a huge amount of effort that went into developing the SambaFlow data flow compilation environment to enable you to take PyTorch ML algorithms and generate configurations that could optimally use the resources of a SN10 and follow-on RDUs. So let's look at how the RDU can execute ML algorithms potentially more efficiently than GPU architectures can. So for that, let's briefly take a look at the architecture of the NVIDIA A100, which is a GPU with 108 streaming multiprocessors, and it's got each of them has 192 kilobytes of SRAM, and then it's got 1.5 terabytes of bandwidth to the off-chip high bandwidth memory, which has a size of between 40 and 80 gigabytes. So if you kind of look at the memory hierarchy as shown on the right, you've got SRAM 20 megabytes with a total of 19 terabytes of bandwidth per second, and then you've got off-chip HBM, 1.5 terabytes per second, 40 to 80 gigabytes in size, and then the whole chip has a peak performance of around 300 teraflops. If you look at sort of how you execute these kernels, you execute them in time, one at a time, and you move data back and forth. If you compare that to what you do with SambaNova, you're going to execute them in space, and you're going to make use of the much larger SRAM on chip, and you're going to make use of the off-chip DDR, but the DDR bandwidth is much less, only 150 gigabytes per second. And so if you lay things out in space, then you get to make use of the on-chip bandwidth, and you make use of the meta pipelining, and what you see is an improvement in performance on sparse matrix computations, and the performance improves, especially in terms of the pipelining, the meta pipelining, as the sparsity increases. And the key reason for this is because by higher sparsity, the impact of the gems goes down, and because you can do the permutation on chip using these data transformation capabilities, you get much higher performance. So if you run attention on the A100, turns out that potentially flash attention increases the arithmetic intensity such that it becomes compute bound, but then of course you run into some of the limitations of the fact that you're running with threads, and so the warp limitations limit you to 100 teraflops on flash attention. The SN10 also is compute limited, but because we have many more resources, we don't have the limit of threads and warps, and we have a lot more bandwidth to the on-chip SRAM and a lot more SRAM, you get higher performance. You also, of course, need to, of course, one chip won't do it. You need to be able to scale to multiple chips, and we do that in a cluster. And then we can also do that by connecting multiple clusters together and making use of the large DRAMs to make it simpler to scale. And we can scale out in a fairly linear fashion with very large models of over 176 billion parameters. So one example of doing this is a foundation model called BloomChat, right, which is a 176 billion parameter model. And this model is an open source model, and we've shown that we can run this model on the RDU, and we released it, and we've shown that it's actually does better at at multiple language models. And so this is something that is being quite important in the open source area. So finally, we want to be able to support both language models and image models, and so you want multimodal models. And again, the large memory is really important here. And in the RDU, the ability to have large memory allows you to support 3D image models or 3D models. And so here we're showing the ability to do kidney cancer segmentation much better using a 3D model that uses the memory of the RDU to get much better segmentation accuracy than you can with the limited memory that you have on conventional accelerator architectures. So in conclusion then, computing in the foundation model era is this co-design of ML algorithms programming languages, and accelerator architectures. So we've talked about subquadratic attention algorithms, block sparsity for ML algorithms, how the importance of new domain-specific languages, data flow compilers, and of course exploiting sparsity in the PL arena, and then accelerator architectures. Key will be ideas in reconfigurable data flow, large memory to support the large parameter models that will be increasingly in use, and potentially new types of compute primitives like FFT could potentially be important. So thank you for your attention, and at this point I'd be glad to take questions.
So there are microphones in the middle. Please walk there. I know it's far. And we'll start with one at your right.
Thanks for the great talk. I'm Rajat from Cornell. So on the languages side, of course, Spatial innovated a lot in order to make it so much more scalable to design these accelerators. I'm wondering, now that the PL community is so much more interested in building DSLs and applying sort of type systems research and semantic models for languages that generate hardware, what do you see as the key challenges in building new programming models that support this kind of new programming models and hardware design techniques? Thanks.
I'm having trouble hearing. Dilma,
I also had a hard time.
Can you just repeat the key substance of the question?
Okay, yeah. What are some of the key challenges on the language design side for programming models for accelerator and designing accelerators?
Oh, key challenges on the programming languages side. So I think one of the issues that we're exploring is sort of with these spatial architectures, right? You both need to do things in time and in space, and you'd like to be able to smoothly decide when you'd like to execute things in time and when you'd like to execute things in space. And we don't really see today any languages that give you that kind of expressive capability. So that's one of the challenges that we think are important on the PL side. And then, of course, it's sort of how do you explore the design space in an efficient way, right? Because the problem with these spatial architectures is you've blown up the number of things that you potentially do at the same time, and figuring out how to chop up your model such that you both fit within the constraints of whatever the resources you have, and also get the best performance is another big challenge.
Thank you.
Now from your left. Yes.
Hi, Kunle. Ben Zorn from Microsoft Research. Thanks for a great talk. Really interesting, great advances in many dimensions. My question is about your thoughts on leveraging the newest language models like GPT-4 to actually help you do design and implementation of hardware algorithms and languages.
Yeah, I think this is a really interesting area. So we've recently hired at Stanford a new faculty member called Azalea Marashani. And, she and I have sort of started to look at this area. I don't have any hard, results, but I think that the notion of using these language models to both do hardware design and sort of design of all sorts of things is really going to be interesting. This whole idea of using ML to improve systems, right? So we've started to look at with Mohammed Shabazz at Purdue, this area, sort of how you do it in the networking arena, right? Where you can think about replacing a lot of the heuristics for security and for load balancing and other sorts of things that you'd like to do with data-driven models. And so I think this is an approach that is going to be useful through all sorts of systems. I think the key thing is sort of how can you find the right sorts of models and how do you train them, right? Because it's problem, figuring out all the different things that you might want to do in terms of designing something for exploring the design space and using that as training data, is probably going to be a challenge, right? So in some of the other work that we've done, that seems to be a limitation is that you don't have as much training data as you might like.
Great, thank you.
From this side,
Karthik Sriram from Yale University. The talk was excellent, and I understood a lot on how we can help scale up these models. Understanding exactly how these large models work and do the things that they do is an important task that a lot of people are working on. Can you comment on how, as system designers and hardware designers, how we can help provide some features to aid this work?
Yeah, I think I'd reiterate what I said in the talk is that you want to create more scalable and efficient systems and flexible systems so that, if you provide only certain primitives that go fast, like dense matrix multiply, then you're kind of limiting the ML researchers to use those primitives, because if they use anything else, they simply won't be able to train large models. So you want flexibility, but you also want to be able to scale, and you want to be able to provide mechanisms and the ability for more researchers to play with these large language models, which fundamentally means you need to bring down the cost of training, which means more efficiency.
Thank you.
back to our lab.
Hi, Kunle. Marcelo from Princeton University. You mentioned flexibility and programmability. In these data flow architectures, I've seen these two trends of CEO functional units like CGRA that you have in Plasticine and SambaNova, but then other trend in like teeny tiny ISA programmable cores. Why is the decision of going for these functional units, which require like upfront configuration rather than ISA programmable cores? Is it the last mile of performance that you're trying to achieve?
Well, I mean, I think the issue is, there's two issues. One is, so you're saying instead of having these dedicated function units, why not just have a bunch of cores?
Like teeny tiny cores, yeah.
Well, so the problem is that if you make the cores too small, they again become inefficient, right? Because the workhorse is going to be some sort of, matrix computation unit like matrix multiply, right? So, you still want to provide that sort of functional unit. And so the question now is how you chain them together. And you want to do so with as lower overhead, the smallest amount of overhead as possible. And you want to allow streaming and meta pipelining. And so the question is, if you put a core in there with its overhead and its programming overhead, is that the best way to achieve what you want to achieve, given that, we've had a lot of experience trying to make cores run efficiently, and it turns out to be pretty challenging.
Thank you.
Hi, Kunle. I'm Priyanka from UMass Amherst. So my question is, in the long term, whether we should focus on efficient general purpose computing or specialized computing as the models keep evolving, like considering the impacts on the environment, like embodied carbon footprint? Yeah.
Well, I think you want to do both, right? We want to eat our cake and have it. We want efficiency and we want flexibility, and so that's why it's a challenging problem, right? Because otherwise, you just be wasteful in terms of your use of resources. And so it's not either or, it's both. And that's what we're trying to achieve with these reconfigurable data flow architectures.
Yeah, I have one more question. So usually you try to improve the computation by first have a best algorithm and then you go down to improve the hardware, or you should first have a good hardware and then you try to improve your algorithm to work it best for the hardware. What's the best approach?
Well, it's a co-design. It goes back and forth, right? I mean, that was you saw that with the flash attention algorithm. You see this with this meta pipeline. You first understand what the bottlenecks are with current hardware. You adjust the algorithm, and then as you move forward, you might decide that you really do need a different algorithm.
Okay, thank you.
Yeah.
Good afternoon. I'm Siddharth from Carnegie Mellon. You mentioned a few times in your talk that FFTs are a challenge for ML accelerators, but could you shed some light on why it's difficult for ML accelerators to do FFTs, especially given that there are a lot of specific hardware that does FFT? Yeah, FFT, it's a log n algorithm, but it requires data movement in what's called a butterfly pattern. And it turns out that this kind of data movement pattern is not well supported on current accelerator hardware. So that's the limitation. It's basically a data movement problem rather than raw flops.
Thank you. We'll do the last question.
Okay, last question.
Hi, this is Henry from Princeton. I'm the lucky one. So I have a question about the memory systems of SambaNova. So if you have a very large language models, like with hundreds of gigabytes of parameters, and if to perform one inference, you need to at least read all the weights from in SambaNova, your DRAM, which has a very limited bandwidth compared to a GPU HBM. So how do you optimize your memory system to still achieve like very high performance in the case you have a lot of ways to read from DRAM?
Yeah, that's a really, really good question. So, the chip that I showed you in the system I showed you was kind of optimized for training, right? Large batch training. If you want to optimize for inference, then you're right. You do need a lot of bandwidth. Now, you can optimize the algorithm, right? So you might know that there's multi-headed attention, but there's also multi-query attention, right? So multi-query attention needs smaller numbers of KV cache parameters, and so it's more efficient. So you can change the algorithm, and actually you can do pretty well. But then ultimately you want to introduce HBM. So stay tuned. We want to add a layer to the memory hierarchy, especially for inference, which is the case that you pointed out. So good observation.
Thank you. Kunle will be around for a little bit, so you can still ask questions. We want to thank Kunle, but also, Tim, you want to give something that you need to say? Better do right now, and then we will thank.
Let's thank the speaker one more time.
Thank you.
So it's now the lunch break. Please exit as fast as you can and orderly as you can. There will be a awards luncheon in Cypress 1, and for the rest of us, our lunch is in Cypress 3. Okay, thank you. The PLDI is in Cypress 1. Awards luncheon.